Hello viewers, welcome to Adam. So now we are going to solve this interesting numerical based on SFD and BMD. As you can see here, we have a AB beam. Between A and C, there is a infinite distributed load. At there is a point load at D. There is a hinge support at A, and there is a roller support at B. So let us see how can we solve this problem. As you know, in every SFD BMD problem, we need to first make the FBD to get the support reactions. Then we need to find the shear forces at every point to make the SFD, and then to find the BM bending moments at every point to make the bending moment diagram. So these are the steps involved. So let us try to follow the steps on that one and to solve the problem. So firstly, we need to make the FBD. So what we have here, let us say this is a beam, our beam, this is AB. So this is C, this is D. We have a point force of 10 kilonewton here. We have UDL between A and C, and at A we have a hinge support. So because of the hinge support, we need to do two forces, which is, let us say, FAY. Let's say this is FAX, and we need to convert the UDL into a point load. Let us say this is 80 kilonewton, because 20 kilonewton, as you can see here, is the magnitude, and the total length is 4. So 20 into 4 is 80. So that is the loading condition, or the loading total load. At B, we have a roller support, so we will only give a vertical force. So FBY. You can see here that what we have done is whenever there is a hinge support, as explained also earlier, that whenever there is a hinge support, we need to give forces in both the direction. That is, let us say, Fy and Fx. If this is the y direction, this is the x direction. And if there is a roller support, let us say this is the roller support, then we need to give force only in the y direction. Let us say this is the y direction, so Fy. And if there is a fixed cantilever beam, so then we have to give the forces in xy and also a moment. So there will be three unknown forces here. There is one unknown force here, and there is a two unknown forces here. So that are the reaction forces which you need to give according to different types of supports. So if you are clear with this, we can just move ahead with our calculation. So we have given for two forces here because of the hinge support, but there is no horizontal forces in the entire beam other than FAX. So let us just apply the equilibrium condition now, which is a summation FAX. Summation Fx is 0, summation Fy is 0, and summation of movement at any point is 0. You also could have noticed that there is a UDL conversion happening here. So how can we convert the UDL? It's very simple. That you just have to integrate the total load which is acting on this. So the 20 kilonewton per meter is the magnitude of the load, and total length is 4 meters. So let us say there is a UDL of length L, and the magnitude is M, or let us say K. Yeah. So the magnitude is, let us say, K. So what you have is the total load can be calculated from this condition, that total load will be K into ds, which means the integration of all the small parts or all the small shear forces that is acting on the beam. So K is constant here, which is the 20 kilonewton per meter. So let us say 20 into integration, this is 0 to L, which is total length of the beam, so which is 4. So it will be 80 as explained earlier, and it will be acting, it can be assumed to be acting on the center of the beam. The center of the beam will be L by 2, which is 2 meter from here and 2 meter from here. So that is how you can convert the UDL into a point load. You just have to find the total load which is acting in, assume that it is acting on the center of the beam. So now let us move ahead with our equilibrium condition. We have Fx is 0, summation of Fx is 0, which only have one forces, so Fx will become 0. Let us say this is equation number 1. We also have a summation of Fy is 0, which will give Fay minus 80, because it is in the downward direction. So for now, let us consider upward as positive and downward as negative. You can change this, it won't affect the solution. So we have minus 80 here, we have minus 10 here, and we have plus FBY here, which goes to 0. So we have FAY plus FBY going to 90 kilonewton. This is our equation, let us say 2. As you can see, there are two variables here, FAY and FBY, and only one equation. So we need another equation to solve this solve for this variable. So the third equation will be coming from summation of moment is 0. Let us calculate moment at any. You can calculate moment at any point for our to make it easier for us to. We always calculate at the moment at a point where the unknown forces is going through. So either we calculate at FBY or either at FAY. Let us say at A or at B, because the moment is nothing but the force into perpendicular distance. So if you calculate at B, so the perpendicular distance for FBY will be 0. So that the moment because of that force will be 0. So it won't be appearing in the equation. So that is why we try to calculate moment at a point where the unknown force is going through, to make the contribution of that force 0, so that we can calculate the second unknown force, which is FAY, which will be directly calculated, and we don't need to complicate the equation further. So for now, we'll just calculate at, let us say we calculate at A to make the FAY invisible. So because the FAY will disappear, and then FBY will only be there in the equation. So let us say FAY we have here, and the equation can be formed like, let us just set up this. So we have about A, let us moment about A, let us say 0. So we have FBY anti-clockwise. So let us take anti-clockwise as negative and clockwise as positive. Again, you can change this, it won't affect the solution. So let us first calculate moment about this, like moment because of this force. So AT into 2 in the clockwise direction, so it is positive. There is also a moment because of this 10 kilonewton force. So this distance is 4 according to the diagram. This is 2. So 4 plus 4 is 8. So 8 into 10 will be again in the clockwise direction, so positive. And the FBY, so because of the FBY into 4 plus 4 plus 2 is 10. So into 10 will be in the anti-clockwise direction, so it will be negative. So equals to 0. So if you take it in the other direction, so 80 into 2 will be 160 plus 80 will be 240. By 10 will be 24. So FBY will be 24 kilonewton. So this is our first equation. And if you put this value in our second equation, which is FAY plus FBY is 90, you can get the value of FAY also, which will be 90 minus 24, which comes out to be 66. You can just, I'll just recheck the first value which we have. 8 into 2 plus 8 into 10 is 240 divided by 10 is 24. So the value is correct. So let us move ahead with our further calculation. We have FAY as 66, FBY as 24. Yeah. So let us calculate shear forces at every point now. So shear force after A, let us calculate after A. So shear force at A is the reaction at A only. So if you just cross check this here, like right after the A, point A. So on the left, you can see only one force, that is the reaction due to A. And that is 66 as we have calculated. So it will be 66 in the upper direction. So for the shear force, if you are considering forces on the left side, which we will always do, so you just have to take the upward at positive and downward at negative. And if you are calculating on the right side of the beam, like considering forces on the right side, then you need to consider upward as negative and downward as positive. So that is the basic sign convention here. We will always be considering this first case, which will be like considering the forces on the left, because it just makes the job easy for us and it doesn't confuse us in the sign convention. So that is why we'll do it. So let us now calculate shear force, the force C, or you can say that left of C, whatever you prefer. So before C, there are two forces. Let us say you can just see over this. Let us just copy this diagram. So see, like you can see here also that the forces on the left of the C are two forces, Fay in the upper direction, which is 66 minus 80 here, because there is a downward force here. So the downward will be negative according to our sign convention, and upward will be positive. So the Fay is 66 minus 80, which will give you minus 40. So minus 14 here. Before C. Let us calculate shear force after C. It will again be minus 14 because there is no sudden change of force at C. There is no sudden force at C like there is at D. Between C and D, there is no shear force. So before D will be also same as after C. So before D will be like the same, which is minus 40. And shear force just right of C, or after C, just right of C, just right of C will be minus 14 minus 10, which is minus 24. And you can also calculate shear force before or just left of B as minus 24 because there is no shear force between D and B, and shear force at B will become minus 24 plus 24 because of the reaction at B, and it will go to 0. So that is how we have calculated all the shear forces. Let us just make the SRF diagram from the above equation or the above values. So we have A, we have C, we have D, we have V. At A, the value is 66. Let us say this is 66. So this is 66, let us say. And before C we have minus 14. Sorry, before C, let us just see the value. Yeah. So before C we have minus 14, and after C also we have minus 14. So before C it will be minus 14. So let's just leave it like this. And before D it is minus 14, and after D it is minus 24. So before D it is minus 14, and after D it is just minus 24 at the same point. So that is the advantage of calculating before and after, that you just know that at what point it will just jump. At before and after calculation just helps in that visualization and make it little bit easier. At B we have minus 24, and after B we have 0. So it will just be 0 there. So as you can see, there will be an inclined line between yeah, so there will be an inclined line between E and C because of the UDL, and there will be a constant line between C and D because there is no shear force between this and this. So it will be 10. So this is how you can make the shear force diagram. So as you could have seen, like wherever there is no UDL and there is just a point forces, we have given a constant load, and as you can see here, and here constant load, and whenever there is UDL, we have given it as inclined load. So that is just a concept you need to like understand, that whenever there is a UDL given, the shear force diagram will be a line or an inclined line, let us say. And whenever there is not, there will be a there will be a constant line. If there is no UDL, there will be a constant line. So this can be understood even further. Let us say there is a triangular node, or let us say uniformly varying node. So the shear force diagram will be parabolic. What happens here is you can understand this by a very simple like memorization, that whatever the degree of load is, the shear force degree will be 1 degree above that. So the degree of load is 0, so it is not changing between this and this, so the degree of load will be 0, the load acting will be 0, so the shear force degree will be 1, which means that it is constant. And whenever the degree of load, so the load is constant, let us say some the UDL, so the load will be constant at that point. So the 1 degree up will be to get the linear line. So this is linear line. The shear force will be a linear line for the UDL. So again 1 degree up, and if there is a uniformly varying load, which is the, let's say mx plus c something, so the shear force diagram will be some parabolic, which is again 1 degree up from that mx square. So the parabola is always mx square plus some b, let us say. So the degree of shear force diagram will be again 1 degree up from the load, whatever the load here, and the degree of bending moment will be 1 degree up from the shear force diagram. So that is just the basic relationship between load, shear force, and bending moment. So all of this are 1 degree up from one another. So the load is at first, then the shear force, then the bending moment. All are 1 degree up from one another. So let us move ahead with the calculation of bending moments. So as you can see, there is a point where the shear force is going to 0. We need to calculate that point also, because the bending moment at that point will be maximum wherever the shear force becomes 0. That is because the shear force can be represented at dm by dx, and from calculus that maximum of this function will be reached where the dm by dx will become 0, which means the shear force will become 0. Then we can say that at that point the bending moment is maximum. So that is from calculus. So whenever you want to find the maximum of some function, let us say m is the function here. So you just equate the differential to 0, which means we also have a relation dm by dx as shear force. So whenever you say that dm by dx should be 0, you also mean that shear force should be 0 at that point to make the bending moment or that function, whatever function it is, maximum. So from that we can say that bending moment will be maximum where the shear force will be 0, or the slope of the bending moment will be 0 at that point. Whereas the shear force is 0, the slope of the bending moment will be 0, which means it will be maximum. You can just remember that to not get confused in the derivation part of it. So yeah, we can move ahead with calculation of that point wherever the shear force is becoming 0, because we need to calculate bending moment at that point also. So what we have here is 66 Newton in the upper direction, kilonewton in the upper direction, minus of 20 kilonewton per meter force into some x distance, which will go to 0. So let us say this is the UDL. You have a 66 kilonewton force in the upward direction, and after some x distance it is going to 0, and then in the negative direction. So let us say we want to find that x. So you can calculate by this equation. So the x will come out to be 3.3. Yeah, so x will come out to be 3.3 from E. So the total is 4 meters. At 3.3 it is becoming 0. So you need to calculate bending moment at that point also, because you know that it will be maximum at this point. So at this point the shear force is going to 0, which means the bending moment will be maximum. So let us calculate bending moment at every point now. So bending moment at, let us say I calculate at A and B will be 0, because again equilibrium condition there. You can just assume that the bending moment at the extreme point of the beam will be 0 always, because of that equilibrium condition, unless there is a fixed load, because the hinge supports and all, there is no movement, so there are just 0 movement. But if there is a cantilever with a fixed support, so there will be a movement at this point also. So unless there is a fixed support given, you can just assume that for hinge and roller support, the bending moment at extreme cases will be 0. So what we have now is bending moment at let us say some x point, which is 3.3. So let us say this is 3.3 from here. So what we have is a 20 into 3.3 load will be acting downward still. Let us say we are calculating bending moment on the left of this. So there is also a cosine convention here. So if you are calculating from the forces on the left, then you need to give clockwise as positive and anti-clockwise as negative. And if you are calculating from the forces on the right, then you have to give clockwise as negative and anti-clockwise as positive. So just the opposite of this, you just need to remember this, that whenever you are calculating bending moment from the left side forces, left side of the cross section, then you just need to give clockwise as positive and anti-clockwise as negative. So that is what we are doing right now, that we are calculating at some point x and considering forces on the left side. So that is why we are given clockwise as positive and anti-clockwise as negative. So let us calculate that. So, the total force will be 20 into 3.3, which will be 66. Yes, yeah, 66. And the distance will be 3.3 by 2, which is 1.65. So 1.65 distance from that x point up to the, because the load will be acting at the center of this, right? So it will be 1.65 from this and 1.65 from this. That is why it is 1.65 from that x point, let us say. So you can just calculate the bending moment at x, which will be, because of A, there will be a clockwise movement, which is positive, of course, because of the sign convention. So at A, there is a 66 kilonewton force acting upwards, which means positive, which means clockwise, which means positive. So it to 3.3 minus 66 into 1.65 because of the UDL. So here 66 into 1.65, which will give you 108.9 as the answer. Yeah, 108.9 is the answer of the bending moment at point, let us say x. So you have to also calculate bending moment at C, let us say. So at C, you can calculate from the right side now, because there are like you can also calculate from the left side also, and or you can calculate from the right side. It's up to you. So let us just calculate on the left side, because we've been doing that. It will be easy for us to like understand or correlate with the previously discussed thing. So what we have here is we have a 80 kilonewton force as it is discussed in the MPT, and there is a 66 kilonewton force in the upward. So this is the 2, and this is the distance is the 2, and this is the distance is the 4. So you can just say that 66 into 4 in the clockwise direction minus 80 into 2 in the anti-clockwise direction. 66 into 4 minus 80 into 2 will give you 104. As you can see, it is lesser than this because this is the maximum. When throughout the wind, this will be always should be maximum, because the shear force is 0 at this point. So you can just cross check your answer by comparing that. Whenever the shear force is 0, your bending moment should be maximum. This is a trick to cross check your answer, final answer. You can just remember this trick. It is very useful sometimes. So bending moment at, let us say you are calculating at D. So I will not now consider on the left because there are too much forces on the left. So I will just consider on the right, which is this B force. So the B force is 24. Yeah, 24 into 2, which will give you 48 as the bending moment at D. And bending moment at B, of course, is 0, as we have discussed earlier. So let us now draw the diagram regarding the same. At A, we have 0. Let us say this is A, this is C, this is D, this is B. So at A, we have 0. It's let 3.3, let us say from X, there is somewhat X, where is there is a maximum, which is 108.9. At C, this is 104. If I'm not mistaken, yes, this is 104. At D, it is 48. This is 104. 108.9, 104. Yeah, this is point. This is the Y. Yeah, so you just need to, like, whenever there is a UDL, you just have to give it a parabolic loading. Here isn't just to be the linear here and linear here. I will just recreate this. Yeah, so this is your bending moment diagram. As you can see, we have given a 1 degree above the SF diagram, the parabolic curve here, because of the UDL was linear. So you can also derive from this equation that dm by dx is shear force. So whenever the shear force is linear, let us say some mx plus c, then you just take it on the right side, the dx, integrate it, and you will get that moment at some mx square plus some d, let us say. So it will be parabolic if the shear force is linear. And if it is constant, let us say, so let us say if now your shear force is some constant c into dx, the moment, which will be the moment, so the moment will come out to be c x plus d, which is linear. So whenever your shear force is constant, your movement will be some linear linear variation, or will be an inclined line, let us say. And whenever your shear force is some inclined line, the movement will be parabolic, where it is parabolic here. So as you can see in the SF diagram, that it was a linear line between E and C. So that is why between E and C it is a parabolic line now. And between CD it was a constant line, between DB it was a constant line. That is why it is an inclined line now. So again it comes back to the same point, that load SF and VM are always 1 degree above the previous one. That is the main concept. So that is how we can solve the question. You can just cross check your answer, and this is the answer which is looking to be correct. So yeah,